Now let's talk about the correlation coefficient of the exact same set of points. Okay, so what are the things that we need here? We need the sum of the xy's. Okay, the sum of the x's and the sum of the y's. So sum of x, sum of y. And then we need, that's it. Okay, so if we go back up, 488, 260. Let's go 488, 260. And then the sum of the xy's is 16,740. 16,740. Okay, now let's just plug in. R equals, so the number of points that we had was 8 times the sum of the xy is 16,740 minus the sum of the x's, which is 48, times the sum of the y's, which is 260. And we're going to do this all over. Remember, there's a huge square root sign here. 8 times the sum of the x's, the sum of the x squareds, sorry, 31,276. $31,276. 31,276 minus the sum of the x's, which is 48, and that squared. Now we do the exact same thing, but for the y. So 8 times sum of the y squareds. $91.36. Okay. 91.36 minus the sum of the y's, which was 260, and then we square that. And extend those. Okay, so now let's actually type in the numerator. 8 times 16,740 minus 48 times 260. I get the 7040. Okay, that's good. Okay. 8 times 31,276 minus 48 squared. For the first thing on the bottom, I get 12,064. And then I get times 8 times 9136 minus 260 squared times 5488. Okay, let's go 7040 on the top, and then root 66, 207, 232 on the bottom. And now let's actually solve. 7040 divided by root 66, 207, 232. I get 0.8652. Now we go back to Excel, we get 0.8652. So that's actually perfect. So all of those calculations were perfect. Okay, we can conclude that this is a positive. I'll just write it here, positive and strong linear correlation. Okay, again, it's linear because we're using y equals mx plus b. Correlate. There we go. Okay, now all this question wants to do now is graph the data and the line of best fit, and then does it work? Okay, do these data support the researcher's theory? So what I'm going to do is I'm going to plot the x versus the y, and then just take a look if the line of best fit is a good line. Okay, so we have x, which is the rabbit population, and then we have the y, which is the wolf population. Okay, and if we take a look at these numbers, The rabbit population goes up to about almost 80, and the wolf population, I think, goes up to 50. So 80 and then 50. So let's see if this works. 10, 20, 30, 40, 50. Yeah, it will. 60, 70, 80. 10, 20, 30, 40. Okay, and then up the side, we'll do 10, 20, 30, 40, 50. I'm going to put this on hold, and I'm going to go ahead and I'm going to graph like 61, 26, 72, 33. All right, so this is what I get when I graph all of these points. And let's actually take a look. So the line of best fit, I would say, which would go through like the middle here. So if we actually read it, it's like 0.58x minus 2.88. So 2.88, it would hit right here. Negative 2.88. And then it would go up ever so gradually. Okay, and then that would be the line of best fit. And we would, of course, label this y equals, and then 0.58x minus 2.88. It was. Okay, and I would say that yes, the data supports the researcher's theory. Okay, as the wolf population depends on the rabbit population. Okay, I would definitely say as the rabbit population increases, the wolf population increases. Okay, as rabbit R increases, the number of wolves increase as well.